Okay guys, today we're going to be looking at the chemistry of haloalkanes or halogenoalkanes. Sometimes you hear it halogenoalkanes, which is generally how you see it written out on all of your materials. So it's the same, it's very basic principle. It's the same kind of thing that we've been doing for the past several days. We're going to look at a specific type of reaction mechanism. We're going to look at the different reagents that are used. We're going to look at the different conditions that are used. Please make sure that when you learn these reactions that you're learning what conditions these things are happening under as well. Feel free obviously to pause at any point. And as you're going through this, just write down any questions that you might have so that you can ask me when I return. But let's get started. Skip this, contents, blah, 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 blah. Okay, so two types of haloalkanes. We've got obviously the haloalkane, which is a halogen attached to an alkane. The four halogens that we're looking at are fluorine, chlorine, bromine, or iodine. The bigger ones don't tend to bond. Haloarenes are halogens that are directly attached to a benzene or an aromatic ring. If you don't remember an aromatic ring or a benzene ring, go ahead and pause now and take the time to go look those up, okay? Let's talk about structural differences. We briefly touched on this in the last class, but we'll come back to it again. So you can label your carbons, carbons are going to be these black dots, as primary, secondary, or tertiary. And it's looking at how many carbons are bonded to whatever carbon you're looking at. So in this case, I'm going to look at this carbon right here with the red dot on it. It has one additional carbon added to it, so it's considered a primary carbon. A secondary carbon has, so here's the carbon that we're looking at. A secondary carbon has two carbons attached to it. And then a tertiary carbon right here has three carbons attached to it. The more carbons that you have attached to that central carbon, the more stable it is. So of the three, the tertiary carbon is the most stable. We've already done naming, so we're going to skip through that. There is structural isomerism based off of both branching and the location of the halogen on the chain. Obviously here we have the halogen at the end. We circle that here. Here we have the halogen at the end. Here we have it not at the end. Here we have branching. Here we have a different type of branching. Okay? So just whenever you're asked to draw a particular structure, make sure to take into account all types of isomerism. All right. Some of the same stuff that we touched on last time. The bigger you get, the higher your boiling point is. The more branches you have, the more condensed you are. So really you have lower boiling point. So the longer your chain is, the higher your boiling point is going to be. The same thing that we were discussing with alkanes, with alkenes, etc. Okay? So we're going to be looking at nucleophilic substitution. So remember the idea of a nucleophile is something that is looking for a nucleus, right? It is nucleophilic, a nucleus lover. All right, so we're looking at any time we've got a carbon here attached to a halogen. Halogens tend to have a much greater electronegativity than carbon, and so it's going to pull this electron cloud away from that carbon, leaving a slightly exposed nucleus. Now, if you have a slightly exposed nucleus, right, and you have a nucleophile, then that nucleophile is going to try and find the nucleus, right? Pretty simple, nucleus, 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 okay? Here are some examples. Let me move this up. Here are some examples of some of our nucleophiles, and these are some of the ones that are pretty common. Notice that these are nucleophiles because they have electron pairs, right? They're going to be an electron pair donor, and those electrons are going to try and find a nucleus to bond with. Okay? So let's see. So here's the mechanism for nucleophilic substitution. Let's move back down here. You've got, again, remember, you've got this great pull of electrons that's happening over here, leaving this nucleus a little bit exposed. So those 2 electrons are going to come down here. Notice it's a double-pronged arrow. 2 electrons are going to bond to that carbon, and these other 2 electrons are going to bump off onto the halogen in this case. Right, so Nu represents my nucleophile, and so I'm substituting my halogen with my nucleophile, whatever it may be. All right, there's some points. You guys can pause and look at this later, so let me move this back up. You hit pause, you write this down, pause. Great, back. Okay. Let's see. Okay, so this is what's called the SN2 mechanism, this nucleophilic substitution. And it kind of works like an umbrella. So you've got, now I wish it would show the full mechanism here, but it doesn't. So what you have, oh, there it goes. Oh, perfect, it does. You see sort of an umbrella turning inside out. This nucleophile is going to approach this carbon, right? You're going to have an intermediate, and then it's going to bounce that halogen off. That's an SN2 reaction. Do I expect you to know this? Absolutely. Okay. All right. The easiest bonds to break are the ones that are really big, right? Fluorine not having a lot of electrons, also not having not having a lot of electrons is going to really hold tight to that carbon. Whereas iodine, for instance, being bigger, is pretty much okay by itself in terms of electrons. So the iodine, even though it's the biggest element, has the weakest bond, which makes it the easiest to break. It's the easiest one to bounce off. So if you're given a choice, if you have CiBrClF as a compound, it'll go for that iodine first. Okay? Okay, so here is an experiment. Okay, sorry. These are just talking about a couple different experiments where you can see the replacement of a halogen. But before we get anywhere near that, I want to get to our actual reaction mechanism. All right, so here's the structure drawn out a little bit nicer for you. This is showing you the OH, right? So O is represented by the red, hydrogens by the white, carbons by the black, and in this case Br, or our halogen, by green. Notice that the Na plus just kind of hangs out by itself in solution. I don't have a pen here, so it's a little hard. And at the end, once you bump that Br off, so now you have a Br minus, right? That Br minus and this Na plus up here are going to combine to make that NaBr. But look at how this reaction mechanism works, right? You're kicking it off on one side, but you're coming in on the opposite side. So I'm going to attack from essentially the back side of this particular carbon, and I bump it off. Again, make sure that you are looking at how many arrows you have here. So this is aqueous nucleophilic substitution of aqueous sodium hydroxide. Notice again, like I told you to, it is aqueous. It's dissolved in water. You have to reflux it, and your product is an alcohol. Okay? Let's see. Is it going to show me? Here we go. Here's another nucleophilic substitution mechanism. So notice there are my 2 electrons. They're going towards the carbon. Those other 2 electrons are bouncing off. And you end up replacing it there. Okay? You get that Br minus. And again, that Br minus is going to attach up with the Na and just be a sodium salt. Okay? Here's the same idea, nucleophilic substitution with potassium cyanide. Again, it's a reflux, and you get a nitrile, because you get that Cn at the end. But again, you're going to kick that Br off in the exact same sequence. Now, if you need to draw this out with the carbons and the nitrogens, etc., go ahead and do that and just hit pause until you can get that drawn out. Your black one, again, here is carbon. Your blue one is your nitrogen. Notice that it's going to be the carbon electrons that are bonding if you think back to the honk rule, because that you have to get the 4 bonds on that carbon. All right. Here we go. This is showing the animated sequence with the potassium cyanide. You've got that carbon, reaches down, it bumps the other 2 electrons off onto the bromine, and then your product there again is the nitrile, plus your bromine ion. All right. Ammonia works the same way. Again, you're in reflux. Notice that it says alcoholic ammonia in excess. This, as far as equilibrium goes, you really want to have a lot of your reactants in order to push this towards our product side. But the same deal happens. You've got the NH3 right here. You've got 2 electrons right there. It's going to bump that off. Now notice that you're left with a positive here and a negative here. Okay? When you do this in the presence of excess ammonia, you can continue to bounce things off. All right? And so you're going to get this now. We're actually going to go back for a second. So here, notice that you have 3. You have NH3 right here. Okay? You're actually going to end with NH2. You're going to bounce one of those hydrogens off. Right? So if you do this, you can replace it again and again and again, and each one of those hydrogens on your NH3 you can replace with an ethyl group. Right? If you just continue this nucleophilic substitution. Okay? Water works the same way. It's a weak or a poor nucleophile, but you can still bump it out. It's a very slow reaction. But the same thing happens. Now remember that you're using the oxygens. Oxygen has 2 electrons. Here's a hydrogen. Oh, it looks just like a really sad person. And here's another hydrogen. Right, and so these 2 electrons are going to be the ones to bounce those bromines off. Right, and so you end up with that OH because you're going to break, just like we talked about last time. Oh, too much. You're going to break along that oxygen-hydrogen bond. All right, so elimination versus substitution. Okay, elimination reactions, you're trying to get rid of something. If your solvent is a water, if your solvent is water, then your hydroxide acts as a nucleophile, right? And so you get that substitution, that nucleophilic substitution like we're looking at, and you get a product. If your solvent is alcohol instead of water, then your hydroxide acts as a base and you eliminate a hydrogen, giving you alkenes, okay? So the solvent that you have here is highly important. All right, let's see how much we can get through. So here's an elimination reaction, right? In this case, it's happening in alcoholic situation. So now this is going to reach for this exposed hydrogen. That hydrogen is going to bounce down here, or those 2 electrons are going to bounce down here. These electrons are going to bounce off, and what I'm going to be left with is a double bond, a water, and my halogen, in this case Br. Okay, that's an elimination reaction. It's that same OH, but because it's an alcohol and not in water, it acts differently. So make sure you pay attention to that. Okay guys, I'm out of time on this, but flip through the rest of this and see if there's anything else that you see. Okay?